This is the 18th lecture on DSP, and our topic today is complementary transfer functions. We continue our discussion on complementary transfer functions, and we introduce the concept of, is an entirely new concept of digital two pairs. In the previous lecture, that was 17th lecture, we continued our discussion on linear phase FIR filters, and we also had a summary. We saw that type 1 linear phase, that is symmetrical impulse response, and odd length, distinguish between length and order. Order is one less than the length because we started 0, n equal to 0. Symmetrical and odd length is the most versatile. Symmetrical even length, you cannot make a high pass filter. A correction which was pointed out by Arpita is that h of z I had written wrongly there as 1 minus z inverse. It should have been 1 plus z inverse. This is type 2. Type 2 has a 0 at z equal to minus 1, and therefore it would be of the form 1 plus z inverse h1 of z. Type 3 has symmetrical impulse response, odd length, and with that you can neither have HPF nor LPF nor BSF, band stop filter, while type 4 asymmetrical even length, you cannot have a low pass filter or a band stop filter. And then we talked about the location of zeros of the transfer function. We saw that the zeros, if they are complex, they have to occur in quads, that is in a group of 4. Exceptions are zeros at plus 1, minus 1, plus j and minus j, and also zeros on the real or the imaginary axis. No, not quite. Real axis. Imaginary axis you still have to have 4, okay, unless they are at plus j or minus j. Agreed. I am glad you understand. Then you talked about complementary filters. Complementary filters are filters the addition of transfer functions of which give rise to what we want. For example, if it is a Delo complementary, then the addition of the transfer function should give rise to a pure delay. Pure delay, the multiplicative constant can be more than 1, less than 1, it does not matter. But in delay complementary, the sum of them should be proportional to z to the minus n0. In all pass complementary, the sum of the transfer functions should be equal to an all pass functions. And whenever we talk of all pass functions, we maintain the discipline that the function is such that its magnitude is 1. All right. Then we talked about power complementary, and in power complementary the sum of the magnitude squared of the transfer function should be equal to the normalized value of 1. All right. And then magnitude complementary, that is sum of the magnitudes should be equal to 1. All right. So these are the 4 types of complementary filters, and we looked at some of them. Delay complementary we talked about, all pass complementary we also talked about. For the particular case of L equal to 2, if H0z is taken as half A0z plus A1z and H1z is taken as half A0z minus this, then their sum obviously is an all pass function equal to A0z. All right. The power complementary, on the other hand, for L equal to 2, we shall have H0z. Well, we shall have H0 e to the j omega magnitude squared plus H1 e to the j omega magnitude squared should be equal to 1, and I told you that by analytic continuation you can extend this to the complete z plane by writing H naught z inverse. After all, with z equal to e to the j omega, this will give you magnitude squared plus H1z inverse should be equal to 1, all right, by analytic continuation. If this is true, then this should also be true for the kind of functions that we are talking about, where analytic continuation is possible. Now, it turns out that these all pass complementary functions are also power complementary. That is, if you take the two all pass complementary functions as H naught and H1, then they are also power complementary, and this can be very easily shown. H naught z inverse is equal to 1/4 A0 z plus A1 z multiplied by A0 z inverse, half we have taken care of in 1/4, plus A1 z inverse. Now, if you multiply them out, then you get 1/4 A0 z inverse, one term. You shall get a corresponding term for A1 z inverse, then A0 z, the cross terms, A1 z inverse plus A1 z A0 z inverse. And it is very easy to comprehend that H1 z inverse, which will involve, instead of a plus sign here, minus sign, here also there will be minus sign, and therefore this term shall remain the same, this term shall remain the same, but this will come with a minus sign and this will also come with a minus sign, and therefore I can write this as 1/4 first term of this above plus second term minus third minus fourth. Do you understand what I have written here? Okay. First term is this, second term is this, third term comes with a negative sign, fourth term comes with a negative sign, and therefore if we add H naught z inverse to H1 z inverse, then the third and fourth terms shall cancel, and inside bracket I shall have 1/4 twice of A0 z inverse, but what is that equal to? 1. A0 z inverse is equal to 1. Similarly, A1 z inverse is also equal to 1. Therefore, I shall get 2 plus 2, which is exactly equal to 1. And therefore, we prove a very important theorem, namely that if H naught 1z, H naught and H1z are all pass complementary, then they are also power complementary. Okay. Therefore, these two transfer functions H naught z and H1 z are very important transfer functions, and they solve many problems that arise in practical applications of DSP. But let us look at first their realization. Well, before we go to the realization, the sum of them is equal to 1. Okay. h naught e to the power. Is that what you are trying to point out?
Is it true for all L? That means all APC?
No, no, not necessarily. Not necessarily. Okay, you shall have to. All right, it's a big question. Is it true for more than 2? Find an answer. Is it yes or no? If it is no, under what conditions shall they be also? Do you understand the question?
Yes.
If 3 transfer functions are all pass complementary, are they also power complementary? Okay. Question, you should answer that. Now, in the present case, we have the power, the sum of the powers equal to 1. Now, if at a particular frequency this magnitude squared is equal to half, let us say at omega equal to omega c, let us say h naught e to the j omega c magnitude squared is equal to half, then does not it follow that h1 e to the j omega c magnitude squared should also be equal to half. So, it would also be true that h1 e to the j omega c magnitude squared equal to half. In other words, at omega c, the 2 transfer function magnitude squared are identical, and therefore, whatever be their magnitude responses, there is a crossover of these responses at omega equal to omega c, all right, and this is called the crossover frequency. And such transfer functions which are all pass complementary as well as power complementary are called crossover networks, crossover networks or crossover filters, and they have a very important application in digital audio. We shall come to this a little later. This frequency definition, crossover frequency, is important. You notice that this is the 3 dB frequency. When magnitude squared is half, magnitude is 1 by root 2, and therefore it is 3 dB below the maximum value. Obviously, if the sum is equal to 1, the maximum of this can be 1, then the other one shall be 0. Maximum of this can also be 1, the other one will be 0, and therefore the magnitudes vary between 0 and 1, and half, magnitude squared equal to half, is midway between them. Magnitude is 1 by root 2, which is 3 dB below the maximum value. Maximum value is 0 decibel. The realization is very simple. Excuse me. What we do is, we have a given input, we multiply by half first. Multiplication by half is no multiplication, it is a shift, all right. And then we have 2 channels. One of them has the all pass filter A0Z, and the other has the all pass filter A1Z. 2 parallel channels, okay, and we add them. If we add them, then you get h naught of z times x of z. Is that clear? The transfer function from xz to this output would be simply half a0z plus a1z. That is h naught of z. And if you multiply this by minus 1, once again this is no multiplication, it is only change of the sign bit. Then you add the 2, then the output that you shall get here is simply h1 of z x of z, all right. Now these h naught and h1 are 2 complementary transfer functions, doubly complementary transfer functions, and all that you require for their realization are two all pass filters. If you can realize two all pass filters, then you can get doubly complementary transfer functions. As an example, suppose H naught of z is our familiar first order IIR low pass filter. If you recall, the low pass filter was 1 minus alpha z inverse, and in the numerator 1 plus z inverse, and the multiplying constant was 1 minus alpha by 2. Why did we require this? To normalize the magnitude to 1, maximum magnitude to 1. Okay? This is in low pass first order IIR filter. Now you can write this as half of 1 minus alpha z inverse 1 plus z inverse. Let us multiply the two numerator factors and write the four terms separately. Then we get minus alpha z inverse. Okay? Now, is that okay? See what happens now. Let me rewrite H naught of z. I will rewrite in a particular fashion now. 1 minus alpha z inverse minus alpha plus z inverse whole divided by 1 minus alpha z inverse. Have I missed a term? No. The first term, first two terms, they make it 1, and then plus minus alpha plus z inverse divided by 1 minus alpha z inverse. Okay. What is this filter? This is an all pass, first order all pass filter. Okay. So we can write this as half. And what about unity? It is a trivial all pass filter of order 0. Okay. So we write excuse me, we write this as A0z. A0z is identically equal to 1 plus A1 of z, which is this first order all pass filters. Why is it all pass? Because the numerator coefficients are reverse order of the denominator coefficient. The magnitude is equal to 1. All right. Now, therefore, my doubly complementary filter of H naught z shall be simply equal to half 1 minus alpha z inverse, and in the numerator minus alpha plus z inverse. And if you simplify this, then you get in the numerator, let me write it on a separate sheet. You get H1 of z as equal to 1 minus alpha z inverse. What shall we have in the numerator? 1 minus z inverse. Is that right?
Yes.
Not quite. No. It shall be multiplied by 1 plus alpha divided by 2. Then the result is correct. Okay? What we get in the numerator is 1 minus alpha z inverse plus alpha minus z inverse, and therefore this is what I get. And you recognize that this is the first order IIR high pass filter, okay, having the same cutoff frequency. What was the cutoff frequency for both? What was the cutoff frequency? Cosine inverse 2 alpha divided by 1 plus alpha squared, and therefore our simplest first order IIR filter, low pass filter, and the simplest first order IIR high pass filter are all pass as well as power complementary. And what is omega c? It is the crossover frequency. Agreed? So, all that you have to do now, realization of A0Z equal to 1 is no problem, it is a straight connection, and A1Z we shall see the realization. We can do this realization by using only how many delays? First order. So, one delay, and we shall show later that we can realize with only one multiplying constant, and that is alpha. All right. So, it is a beautiful set of filters, first order, low pass as well as high pass, realized with one delay and one multiplier, very economic, most economic realization of two doubly complementary filters. Why are they important? Okay, if you plot the magnitudes, one will go like this and the other will go like this, where this is 1 and this is 1 by root 2 and this is omega sub c. Why is this important? Okay. This is one of the most used doubly complementary filters in the industry, digital audio industry. What they do is, in producing a stereo music or speech or whatever it is, what they do is they record and then they record a single waveform or a single signal, then they separate into two. One accentuates the high frequencies, the other accentuates the low frequencies. The simplest digital stereo. There are other processing in between. Okay, for example, if you want to enhance the baya sound in a tabla baya combination, then you have to use other filters, but this is the simplest. If you take a music and separate them by means of these two crossover networks, implemented most economically by a single chip which contains a realization of the first order all pass filter with one delay and one multiplier, then you get a simple digital stereo. Okay. So, this is one of the most used set in industry. We next consider a magnitude complementary filter. Magnitude complementary filter. Again, if we take a set of 2, then G0 e to the j omega magnitude plus G1 e to the j omega magnitude should be equal to 1. All right. Now, a very simple example of this would be if G0Z is equal to, we take the doubly complementary filter half A0 plus A1, half A0 minus A1, and if we make Z0 is equal to H naught Z squared and G1Z equal to H1Z squared, then you know that H naught e to the j omega magnitude squared plus H1 e to the j omega magnitude squared is equal to 1. If you take that set, half A0 plus minus A1, and therefore G0 and G1 shall be magnitude complementary. And you can, is this point clear? That if you take the square of these two, after all they are power complementary, and what is H naught e to the j omega squared magnitude? It is the same as magnitude of e to the j omega squared. Agreed? And therefore the sum shall be equal to unity. No, It is true at all frequencies, because H naught magnitude e to the j squared plus H 1 magnitude squared is equal to 1. So, we took the doubly complementary set H naught and H 1 having half A 0 plus minus A 1, and therefore, they are power complementary, and this is also the magnitude of G 0 of Z, because we have chosen G 0 to be equal to H naught squared. Agreed? And what is H naught squared? H naught Z whole squared this will be 1/4 A 0 squared Z plus A 1 squared Z plus twice A 0 Z A 1 Z. And similarly, G 1 Z shall be equal to 1/4 this plus this minus twice A 0 Z A 1 Z. A question: what can we say, if at all we can say anything, about G 0 and G 1? They are magnitude complementary by design. Are they all pass complementary? If we add them, do we get an all pass filter? Not necessarily. In general, no. Are they power complementary? No. They are magnitude complementary. Okay? So, having a triple complementary filter, unless you take very trivial examples, is a very difficult problem. Okay. So, is there any question on this? On the magnitude complementary? We just took a simple example from what we already know. And getting a magnitude complementary filter is also not a problem. What you do is you cascade the two such blocks, the blocks which realize H naught and H 1, that is, you start with the same all pass filter. One is 1 and the other is minus alpha plus Z inverse divided by 1 minus alpha Z inverse, and we showed how to realize H naught and H 1. Just add one more of this. In other words, it is a modular implementation. If you can make an IC chip for the doubly complementary filter, you just have to repeat the process. It is also a very economical process. If the IC processing fabrication steps have been standardized, you just repeat this without any change, and therefore, you can make a cascade of two such filters to get H naught square and H 1 squared. In between, if you have two such blocks. In between, you get a low pass filter, you get a high pass filter, and you get a set of magnitude complementary filters also. So, it is a versatile chip, okay, having a number of output pins. One will be marked low pass, one will be marked high pass. You can also get an output from the first order all pass filter. So, you also get a first order all pass, first order high pass, first order band pass, and in addition a set of doubly complementary filters and a set of magnitude complementary filter. Okay. We shall come back to complementary filters at a later date, and we shall show why we are obsessed with all pass filters. You have seen one of the examples here, that all this versatility of an IC chip requires a design of a single all pass filter. And if alpha is variable, what is alpha? Alpha is a multiplier. Then all of these filters are variable filters. They can be you get a single chip, then you program for alpha, and you get a programmable versatile chip which gives you all these functions, low pass, high pass, all pass. We will show later, you can also get a band pass, we will show later, and a set of magnitude complementary and doubly complementary filters. We next come to the concept of digital two pairs. Digital two pair. This is defined in analogy with analog two ports. In an analog two port, you have an input applied between two terminals constituting a port and an output between two other terminals constituting the second port. So, you have analog two port. In a digital device, since we are only talking of numbers, what we have is you have an input x of n and you have an output y of n. If a digital signal processor has one input and one output, the chip that I was talking of a minute ago obviously had one input and multiple outputs, SIMO, single input, multiple output. This is an SISO device, single input, single output device. Okay. If we consider a DSP which has two inputs, now we shall show the inputs not in the time domain but in the z domain. Two inputs x1 of z and the other input is x2 of z. For reasons to be made clear at a later date, we draw the two inputs on the two sides. There is no port concept in DSP. You just extract some numbers or you feed some numbers. Okay. This is a schematic representation and the outputs are like this, y1 of z and y2 of z. Then such a device, inside the DSP we shall have simply multipliers and adders, that is all. Okay. Multipliers, adders and delays. Delays means retrieval from the storage. Okay. Such a device having two inputs and two outputs is called a digital two pair. We shall represent it by 2p, or in short a D2P, where P stands for pair and not port. Okay. Port is an analog word, we divorce that word from now. We do not have a concept of a port in DSP, it is a pair, D2P. Let us consider a D2P having the defined inputs x1, x2 and y1, y2. These are functions of z, not n. So, capital, all symbols are capital. It can be characterized, this digital two pair, in analog two port we characterize by z parameters, y parameters, h parameters and ABCD parameters. Okay. In a digital two pair we can characterize this in two different useful ways. There are many ways you can characterize. After all, there are four variables, so you can make all kinds of combinations, but the ones that are useful in practice are that y1 and y2, the two outputs, if you express this in terms of the two inputs x1 of z and x2 of z, then these parameters are called transmission parameters. Obviously, the output is related to the two inputs, so you find out how the two inputs are transmitted to the two outputs. Since they are transmission parameters, this matrix is called a T matrix, capital T, and the parameters themselves are denoted by small t, T11, T12, T21, T22. These T's are transmission parameters. If we write the complete equations, we shall get y1 of z equal to T11 x1 of z plus T12 x2 of z, and y2 of z shall be equal to T21 x1 of z plus T22 x2 of z. Exactly as in analog 2 ports, you can define the parameters, the constants T11, T12, T21 and T22 as T11 obviously is y1 by x1 with x2 equal to 0. If you go back to the schematic diagram, x2 is clamped to 0 and y2 is left arbitrary, apply an x1 and find y1. Similarly, T12 is y1 by x2 under the condition x1 equal to 0, T21 is equal to y2 by x1 with x2 equal to 0, and finally T22 is equal to y2 by x2 with x1 equal to 0. There is no concept of impedance or admittance or whatever it is. These are pure numbers, okay? It is just the ratio of the numbers. But you see, this has been defined in analogy with analog 2 ports. The other way that one can characterize a D2P x1 y1 then y2 x2 is to take the parameters on the left hand side, the variables on the left hand side, and relate them to the variables on the right hand side. Okay? That is, you write x1 y1. There are other combinations. This is the second combination which is useful. x1 y1 is related to y2 x2, and in analogy with analog 2 ports, where you relate V1 I1 to V2 minus I2, if you remember, in analogy with that, these are defined as the ABCD parameters. ABCD parameters in analog 2 ports relate the output quantities, that is V2 and the current I2, but with a negative sign. There is no concept of negative sign here. I am pointing out the differences clearly so that you are not under the misconception that they are identically the same. No, there is no concept of voltage or current or whatever it is, they are pure numbers. But this is defined as ABCD, and in relation and in similarity with analog 2 ports, these are called the chain parameters. Why are they called chain parameters? Because if you have a chain, if you have another D2P here, then Y2 acts as the input and X2 acts as the output at the left hand side, and then you have Y3 and X3, and the overall ABCD parameter of the cascade shall be the multiplication of the 2. This is why they are called chain parameters. And similarly, if you write the chain parameters, x1 is equal to a y2 plus b x2, y1 is equal to c y2 plus d x2, you can now define or measure ABCD parameters. A, for example, shall be x1 by y2 with x2 equal to 0, and so on and so forth. It is the symbol that is given for this matrix ABCD is gamma, capital gamma. Do not confuse between capital gamma and capital T. Capital gamma, one of the hands is chopped off from T. Okay? Distinguish between T and gamma. T is the transmission matrix and gamma, capital gamma, is the chain matrix or the matrix of chain parameters. Obviously, since the variables are the same x1, x2, y1, y2, these parameters should be interrelated to each other, and the interrelationship is that T11 is C by A. You can show this very easily. All you have to do is take this set, express x1 in terms of y1 and y2, similarly express x2 in terms of y1 and y2. No, it is the other way around. You have to express y1 and y2 in terms of x1 and x2. From this set, then you get T parameters in terms of the chain parameters. T12 is equal to AD minus BC. This algebra I leave to you. T21 is equal to 1 over A, and T22 is equal to minus B by A. Similarly, the ABCD parameters can be expressed in terms of T parameters, and the relationships are that capital A is equal to 1 over T21. That should obviously be true because T21 is 1 by A. Capital A should be equal to 1 by T21. B is equal to minus T22 divided by T21. One thing that you should observe, there is a difference between seeing and observing. One thing that you observe is the denominator is the same for all the 4 parameters. This is true in any conversion. Even in analog, it is true. The denominator is the same. Here also T21, T21, then C is equal to T11 by T21, and D is equal to T12, T21 minus T11, T22 divided by T21. Now, there is a concept of reciprocity as in analog 2 ports. In analog 2 ports, the reciprocity says that if the input and output are interchanged, then the ratio should remain the same if the network is reciprocal. Here also, in terms of the T parameters, T12 and T21 relate input and output, and T21 is input and output with interchange. So, a digital 2 pair is said to be reciprocal if T21 is equal to T12, which in terms of the ABCD parameters, if you look at the parameters, if these two are equal, then AD minus BC should be equal to 1. Okay. So, the alternative is or AD minus BC is equal to 1. All right. Now, exactly like analog 2 ports, we can cascade digital 2 pairs in 2 ways. You see, if you take a digital 2 pair, there is nothing sacred about well, let us say the usual ABCD parameters, x1 y1 is equal to ABCD, x2 y2 x2, upper one is y2, and if you cascade another D2P, then I have told you that gamma 1 and gamma 2 multiply to form gamma. Okay. This is why these are called chain parameters. But there is nothing sacred about drawing this input on the right hand side. I could also draw it on the left hand side. If I do that, if I make a cascade like this, number 1, the outputs are going out, and then we have a digital 2 pair number 2, then how do we find the overall parameters. Which parameters shall be relevant? Obviously transmission parameters x1, x2, y1, y2 are being expressed in terms of x1, x2. So, the overall transmission parameter T shall be equal to the product of T1 and T2, all right. Does it matter whether they are cascaded like this or 2 comes first and 1 goes later? The order of cascading is not important. This is called gamma cascade. Unlike analog 2 ports, cascading can be in 2 manners, gamma cascade and this is called T cascade. There is no concept of T cascade in analog 2 ports. Okay. We shall see later how these concepts are useful, the cascading of 2 networks. One you have already seen, cascading of 2 doubly complementary filters gives rise to a magnitude complementary filter. Okay. Finally, we come to the concept of a terminated digital 2 pair. That is, I have a digital 2 pair whose input is x1, first output is y1, then you have y2, x2. If these 2 terminals are terminated, that is, if you use to connect these 2 a transfer function g of z, then it is called a terminated digital 2 pair and it behaves like an SISO system, all right. It is an SISO system and the transfer function y1 by x1, if you describe it by t parameters or ABCD parameters, you should be able to find out, because the constraining equation is that x2 equal to g times y2. So, if in those 2 linear equations you inject this constraint, then you shall be able to find y1 by x1 and they are given by a very similar relationship as in analog 2 ports, C plus D, again the algebra you can work out, C plus D g of z, then A plus B g of z. Or if you use the t parameters, then T11 plus T12 T21 g of z 1 minus T22 g of z. The concept of digital 2 pair shall be utilized to derive canonic realizations of all pass filters at some later date. What is a canonic realization? A realization which uses the minimum number of delays as well as multipliers. The example that I cited, that is the first order all pass filter realized with 1 delay and 1 multiplier, is a canonic realization, and we shall derive the canonic realization from the concept of digital 2 pairs. We shall also use digital 2 pairs at a later date in some other context. Finally, in this class we go back to a discussion of stability, and the reason we go back to stability is that stability can now be, we have examined stability in 2 contexts. One is, we have said that an LTI system is stable if and only if its impulse response is absolutely summable, that is, summation mod of h of n should be less than infinity. The other context we have seen is that the poles should be inside the unit circle, that is, if the poles are p sub I, then p sub I in the z plane should be bounded in magnitude by 1. Now, this is okay, but as far as testing is concerned, if you are given a very high order IIR transfer function, do you ever have to test an FIR for stability? FIR for stability? No, because where are the poles of FIR? They are all at the origin. Origin is deep inside the unit circle. You cannot go more inside the unit circle. So, no problem FIR, but FIR is therefore unconditionally stable. Unconditionally stable. This is one great advantage of FIR, and the other great advantage is that it can give linear phase. These are the two virtues for which FIR is given great respect. Okay, but at the same time, every positive thing comes with its own disadvantage. Disadvantage is that you have to increase the complexity. You have to use a high order FIR to achieve what can be achieved by a second order IIR. All right. So, there are positive and negative points, and the two together make life comfortable. Okay. Now, stability we have considered in terms of these two contexts. One is in the time domain and the other in the z domain. All right, from the location of the poles in the z plane. We now want to see how to test for stability. If you are given a high order filter, high order IIR filter, FIR is no problem, then if you want to test in the time domain, then you have to find h of n, and finding h of n means that you have to invert the z transform transfer function, and inversion of z transforms is a laborious process, particularly if you have multiple poles. All right. Or alternately, you can have the transfer function h of z and factorize its denominator. Okay. Factorizing the denominator itself requires another subroutine, a pole or root finding program, and root finding programs have their own disadvantages. All right. For example, numerical inaccuracy. Any root you cannot find up to infinite number of decimals. You truncate somewhere, and then you go and happily design the filter. Oh, my filter is stable, and then the filter starts oscillating. All right, because of quantization errors. No number except for simple cases can be represented exactly with a finite number of bits, and therefore now besides implementation, this itself is a laborious process to find the roots and then test whether the root is bounded by unity or not. If it is a complex root, complex pole, then you have to find the magnitude and see whether it is inside the unit circle or not. So, but then testing for stability becomes very easy through an algorithm in terms of, again, our obsession, all pass filters. That is, given at h of z to be tested, we first construct an all pass filter, and then you shall see that by a simple algorithm, the derivation of which may not appear that simple, but the end result is simple, you can test the stability without finding the roots, and that algorithm simply means a recursion, implementing a recursion equation. No root finding is by recursion. You cannot do it by recursion, but stability testing can be done by recursion. Let us take the simplest possible IIR filter. Simplest possible is first order. First order IIR filter is no problem. You have 1 minus alpha z and a numerator which can at the most be of order 1. The pole is at z equal to alpha, so it is obvious given a first order. But suppose you have a second order IIR filter, sum n of z 1 plus d1 z inverse plus d2 z to the minus 2. How do you test the stability of this? Obviously, this is also not a problem. You can find P1, 2, the poles, as minus d1 plus minus square root of d1 square minus 4 d2 divided by 2, which is equal to minus d1 by 2 plus minus square root of d1 by 2 whole squared minus d2. Now, once again you will have to find these roots, okay? And again numerical accuracy or inaccuracy does come in. But given d1 and d2, can you say immediately whether the filter is stable or not? This would be possible if we can have a plot of d1, d2 versus d1, if we can demarcate a region in this plane, d1, d2 plane, it is a parameter plane, such that inside this region the second order filter is stable, then you do not have to find the roots. Given d1 and d2, you can immediately say whether they are stable or not. We shall show in the next class that this region is bounded by plus 1 and minus 1, and that the region is like this. That is, within the complete region, this is minus 1 and this is plus 1, this is plus 2 and this is minus 2, we shall derive that this is the region within which, this triangular region is the region within which if d1 and d2 lie, the filter is stable. If d1 or d2 goes outside this range, if the combination, if the d1 d2 point, so d1 d2 will be a single point in this plane. If the point goes outside this triangle, it would be unstable. Not only that, we shall show that if d1 and d2 lies within this red hatched region, then the roots poles shall be complex. On the other hand, if it lies outside, then the poles would be real. The derivation is not available easily in textbooks, and I shall do it completely in the next class, and that is where we close today.